Welcome dear learners. We are continuing Unit 1, Chemistry as a Science Discipline and Scientific Analysis. In this module, we are discussing errors in quantitative chemical analysis. Here we discuss definition of errors, type of errors, that is determinate and indeterminate errors, their difference, etc. Now, constant errors and proportional errors. First of all, we are discussing errors. Definition of errors. You are familiar with accuracy in analysis. An accurate measurement is associated with minimum error. That is, there is an inverse connectivity between error and accuracy. Higher the accuracy, lesser will be the error and vice versa. So, we can define error like this. Measurement invariably involve errors and uncertainties. It is impossible to perform a chemical analysis that is totally free of errors or uncertainties, even though a sharp instrument with a trained analyst, etc. are the conditions. In that case also, there may be a chance for existence of errors as well as uncertainties in a measurement. Now, in analytical chemistry, error is defined as the difference between a measured value and the true or accepted value. In a simple sense of experiment, suppose you are provided with 5 molar NaCl. Its concentration is exactly known. It is 5 molar NaCl. You can use any analytical procedure to find out its exact concentration. You can also use some instrumental methods like spectrophotometer, atomic absorption spectroscopy, etc. to find out the concentration of the metal ions present in the given NaCl solution. And the value is fixed as 5 molar. Suppose in a particular quantitative analytical procedure, you got a value 4.8. So, true value is 5 molar and you got a value which is equal to 4.8 molar. There is a difference of 0.2 molar. This is a considerable difference. That means the error is considerable. You cannot neglect that error. The result is not accurate. Higher the error, lower will be the accuracy. So, simply, error can be defined as the difference between measured value and true value or the accepted value. It can also refer the estimated uncertainty of a measurement or experiment. Higher the error, higher will be the uncertainty in measurement. Now, in measurements, any difference between the measured value and the true value is termed as the error. Accurate measurements associated with the minimum error and errors in analysis are caused by faulty calibrations or standardizations or by random variations and uncertainties in results. These parameters are generally the cause of errors that may occur during a quantitative analytical measurement. We can only hope to minimize errors and estimate their size with acceptable accuracy. It should be noted that it is not possible to eradicate errors completely. We hope that we can minimize errors and estimate the size of errors with acceptable accuracy. It is not at all possible to eliminate every kind of errors. That is, error-free analysis is only theoretically possible, practically it is impossible. Now, absolute and relative error. In the last module, we just mentioned about the concept of absolute and relative error. The present module is a detailed study of various kinds of errors. So, prior to discussing various kinds of errors, we have to first familiarize and revise the concept of absolute and relative error. First of all, absolute error. Absolute error measures the difference between the measured value, which is abbreviated as x measured or chi measured, and the true or accepted value, which is abbreviated as x true. From this equation, it is clear that the absolute error is a modulus. That is, we are considering only the difference, the magnitude of the difference. So, absolute error equal to x measured minus x true. It is the difference between true value and the measured value. And we are considering the positive part only. That is, the absolute error is a modulus, is a positive quantity. Now, a simple example illustrates the concept. If the true weight of a substance is 50 gram and the balance measures it as 49.6 gram, simply take the difference to find out the absolute error. Absolute error in the present problem is 49.6, that is the measured value, minus true value, that is equal to 50. Take the modulus only. So, you are getting 0.4. The difference is actually minus 0.4. Since we are taking only the magnitude, we got the final value as 0.4. Now, the second type of error, that is relative error. Relative error of a measurement is exactly the absolute error divided by the true value. Absolute error is equal to the modulus of the difference between experimental value and the true value. That quantity should be divided by the true value to get the relative error. It may be expressed in general as a percentage by multiplying with the 100. Sometimes it can be expressed as parts per thousand by multiplying with the 1000, or in very rare case, it is expressed as parts per million by multiplying with the 10 raised to 6. This all depends on the magnitude of the result. If the relative error is very small, then you can express it as in ppm. If it is considerably small, you can express it as parts per thousand. If it is small, then you can express it as a percentage. Now, the formula for relative error, this is a familiar concept to you. Relative error is given by absolute error divided by true value. The numerator represents modulus of difference between measured value and the true value, that is absolute error. Numerator represents absolute error. You have to divide it with the true value to get the relative error. I already mentioned the fact that relative error can be expressed as percentage, parts per thousand, parts per million, etc. If it is expressed in percentage, you can call it as relative error percentage. So, relative error percentage is absolute error divided by true value multiplied with 100. To express relative error as parts per million, you have to multiply with the 10 raised to 6 instead of 100. In order to express it as parts per thousand, you have to multiply with 1000 instead of 100. This is simply relative error percentage. So, you have to multiply with the 100. So, this equation is most important. Relative error percentage is equal to the numerator part is absolute error, that is absolute error divided by true value multiplied with the 100. Now, a simple example is here to illustrate the relative error. If the true length is 100 and a measurement gives a value of 98.5, you simply take the difference. The difference is 100 minus 98.5, or take the opposite difference also, 98.5 minus 100. The modulus is equal to 1.5. That 1.5 divided by, you have to multiply with the 100 divided by 100 into 100. So, the final result is 1.5 percentage. If it is expressed in parts per million, you have to multiply with 10 raised to 6. For parts per 1000, you have to multiply with 1000. So, you can express it conveniently in percentage, in parts per 1000, in parts per million, etc. depending on the quantity under your consideration. Now, we are discussing different type of errors. This is a very important core part of this discussion, and we are focusing on several kind of errors that may occur during quantitative analysis. Chemical analysis are affected by at least two important type of errors. These two errors are, first one, systematic error. The systematic error is otherwise called determinate error. Everything is there in this title. Determinate error means you can determine the quantity of the error such that it is possible to rectify that error. However, the second category of error is nothing but random error. The random error is otherwise called indeterminate error. It is not possible to find out the exact reason behind indeterminate error, and also it is not easy to quantify or rectify the random errors. So, systematic or determinate errors, the source can be determined, quantity can be determined, and you can correct it to certain extent. However, random errors or indeterminate errors are difficult to evaluate and difficult to rectify. There is a third type of error which is also possible in quantitative analysis. That type of error is termed as the gross error. So, one broad way we can say that there are three types of errors in quantitative chemical analysis or in measurements of a physical quantity. The three errors are systematic error, random error, and finally the last category, gross error. But we are always giving maximum priority to the first two types. They are systematic error and random error. As far as your syllabus is concerned, we have to focus much more on the systematic error as well as the random error. I have introduced this gross error for familiarization. So, we can move on to details of such errors. Systematic error, as I mentioned, it causes the mean of a data set to differ from the accepted value. Systematic error leads to difference between true value and the experimental value. In the case of random errors, this causes the data to be scattered more or less symmetrically around the mean value. That is, there is a mean experimental value, but the other values are scattered around the mean value. This you can easily identify with the help of graphical representation. More details can be in coming modules. So, systematic error is there, random error is also there. I just mentioned one more error, that is nothing but the gross error. Gross error differ from indeterminate as well as determinate errors. That is why the gross error is established as a new category of error. Even though it is not popular when combined with the determinate and indeterminate errors, gross error is also possible. Gross error may occur in certain cases. We are now discussing something more about this gross error for the sake of convenience. So, gross error differ from indeterminate and determinate errors. They usually occur only occasionally, are often large, and may cause result either high or low than the true value. That is, the gross error may cause higher value than the true value, or we will get some values which are lower than the true value. So, there is a possibility to get higher values as well as lower values. Now, they are often the product of human errors. Human errors contribute to gross error. Gross errors lead to outliers, results that appear to differ markedly from all other data in a set of replicate measurements. I just mentioned the concept of outliers. Suppose we have acceleration due to gravity measurement by simple pendulum experiment. You know, the true value of acceleration due to gravity is 9.8. In some measurements, using simple pendulum experiment, I got a set of values and the values are shown here: 9.79, 9.81, 9.82, 9.78 and 9.1. You look at these values, the last value is 9.1. That value is far away from all these values and far away from the true value. So, excluding this 9.1, the values are more or less accurate as well as precise. But the last value 9.1 is far away. It is against precision as well as against accuracy. That value is considered as outlier in a measurement. That is the concept of outlier. So, suppose you are getting another big value 11 or 10.5, that can also be considered as an outlier. So, you have to keep the fact that gross errors lead to outliers, results that appear to differ markedly from all other data in a set of replicate measurements. Now, we are discussing the first category of errors, that is nothing but determinate errors. Determinate errors are also known as systematic errors. They have definite value and an assignable cause. This is the most important peculiarity of the determinate error. It is having fixed value or definite value and there do a perfect cause, there do a reason for the determinate error. You can assign that, you can find out that reason and to some extent it can be rectified. Now, they are of the same magnitude for replicate measurements made in the same way. Now, they lead to bias in measurement results. There are three important types of systematic errors. That is, it is possible to classify determinate or systematic error into three categories. What are three important categories of determinate errors? The first category is instrumental error. The second category is error due to method or method errors. The last category is personal errors. So, the determinate errors or systematic errors can be broadly divided into three categories. They are instrumental errors, method errors and personal errors. The first category, instrumental errors. We have to consider somewhat more detail about these three kind of determinate errors: instrumental, method as well as personal. So, out of it the first category here looking now, that is instrumental errors. The instrumental errors are caused by non-ideal instrument behavior, by faulty calibration or by use under inappropriate conditions. For example, you can use a pH meter to measure the pH of a solution. You know about the pH value. For pure water it is equal to 7 at 25 degrees Celsius. So, you are measuring the pH of a solution by using a pH meter. Suppose if there is high temperature fluctuation, if there is high voltage fluctuation, due to some reasons, due to inadequate calibration, you have to calibrate the pH meter by using a standard solution of known pH. For this, you have to take a solution with the exact pH value 7.2 and calibrate by setting the machine 7.2 for the standard. You have to make some calibrations, etc. So, if you are not performing a calibration and temperature fluctuation, voltage fluctuation, etc. are there, you can call such a condition as inappropriate conditions. So, when you proceed with that conditions, the value, the measured pH may not be accurate. It may deviate from the considerably deviate from the actual value. So, that is known as the instrumental error. The second category is method error or error due to method. The non-ideal chemical or physical behavior of the reagents and the reactions on which an analysis is based often introduce systematic method errors. This is called error due to method. Impure reagent or presence of impurities in the reagent, inappropriate reactions, not well-defined reactions, etc. may interfere with the analysis. So, such kind of errors are called method errors or error due to method. The sources for non-ideality may include the following things: the slowness of some reactions, the incompleteness of some other reactions, the instability of some chemical species obtained during the reaction, the lack of specificity of most of the reagent, and the possible occurrence of side reactions. So, these are all non-ideal conditions, and these conditions leads to method errors or error due to methods will be obtained there. Now, errors inherent in a method are often difficult to detect. Compared to personal and instrument errors, these method errors are difficult to find it out. And hence, these errors are usually most difficult to identify and correct. We know in general about the systematic errors that the systematic errors can be identified, source can be predicted, you can rectify it to some good extent, but among the three kind of systematic errors, that is personal, method and instrumental errors, this category, the method errors are most difficult to identify and correct. The last category of systematic errors, that is nothing but the personal errors. The personal errors results from carelessness, inattention or personal limitations of the experimenter. The vision, the attention, the physical stability, etc. of the analyst has crucial impact in generating the personal errors. Many measurements require personal judgments. If we fail to judge a particular measurement properly, then it may lead to personal errors. A universal source of personal error is prejudice or bias. Number bias is another source of personal error that varies considerably from person to person. In certain cases, the analyst is unable to exactly read the number, exactly measure a particular value from an instrument, from a reading, or unable to take a perfect reading. Even this is possible when we are taking the titration. When we are doing the titration and take the burette reading, this situation may occur, some parallax error. Some pupils not measure the values accurately. Such kind of errors are called number bias. Also common is a prejudice favoring small digits over large and even numbers over odd. This kind of prejudice is known as number bias. discussing the second most important type of error, that is nothing but indeterminate errors. What are indeterminate errors? Indeterminate errors has a synonym, that is nothing but random errors. These are errors that arise from unpredictable and uncontrollable variations in experimental conditions or measurement process. These kind of errors are unpredictable, and hence to some extent these errors are not rectifiable. These errors cause measurements to fluctuate randomly around the true value and cannot be completely eliminated, but to some extent you can minimize it. Eradication is not possible, but you can minimize it. These errors do not follow a consistent pattern or trend. Sometimes the values may be higher, in some other case the measured values may be low, but these higher and low values show some distribution around a central average. They can cause measurements to be higher or lower than the true value. How to minimize indeterminate errors? I mentioned the fact that the exact reason and exact quantity of indeterminate errors is not possible to figure out, and hence it is too tough to eliminate the indeterminate errors. However, there are certain chances to minimize the indeterminate errors. While indeterminate errors cannot be completely avoided, their effects can be reduced by the following. First one, repeating the measurements. You can take more and more reading again and again under same conditions, such that you can find out the variation in the results. Now the next possibility to minimize the indeterminate error is improving instrument quality. This is another way to reduce, to minimize the indeterminate errors. Controlling environmental conditions like temperature, pH, voltage fluctuation, etc. is another possibility to minimize the indeterminate errors that may occur during an instrumental measurement. Training personnel is a good alternate to minimize these kind of indeterminate errors. The analyst should be trained well before he or she enter to perform the analysis. Now, constant errors. This is another category of systematic error, but we are usually using it in some other context. We have to consider two other kind of systematic errors, such as constant error and proportionate errors. We are first focusing on constant errors. Constant and proportional errors are two special type of systematic or determinate errors. We studied three major type of systematic errors like personal error, method error, instrumental error, etc. This is another classification. Another classification of systematic error is constant and proportional error. We can have more details of constant and proportional error now itself. So, first of all, you keep in mind the fact that constant and proportional errors are two types of systematic or determinate errors. Constant errors remain the same regardless of the size of the measured quantity. If you are measuring a small quantity or big quantity or anything, the constant error has constant magnitude regardless what is the size of the measured quantity. We can exemplify it. Now, these errors are additive in nature. This may add together or additive in nature. They introduce a fixed bias in the measurement which affects all readings equally. This point is very important. This constant error affects all readings equally. Some examples are here. The most common situation is shown here. the excess of reagent need to bring about a color change during a titration. You know about the end point in a titration. In order to get to the end point, you have to add 1 or 2 drops of excess reagent or the titrant. So, the reagent that you have to add in excess is same in all titrations. So, that volume error is constant in all titrations, all titrations of a fixed category. For example, you are doing permanganometric titrations. You have to add 1 or 2 drops of potassium permanganate in excess to find out the end point by noticing the appearance of a pale violet color. So, the extra quantity you have to add to get the end point is constant in all type of permanganometric titrations. A weighing scale that consistently reads 0.5 gram higher than the actual mass. Suppose I am measuring the weight of a pen. The actual weight is 5 gram. So, the error of the instrument is 0.5 gram more. So, I go to the result of 5.5. Instead of that, I am taking the measurement of a 50 gram sample. I got the final result as 50.5. Here also the error is 0.5. If I am doing this measurement with a 100 gram sample, I go to the value 100.5. So, whenever I measure 3 times 3 different objects, the extra weight that is offered by the weighing scale is constant, that is equal to 0.5. So, irrespective of the quantity you measure, this weighing scale offer a fixed high error of 0.5 grams. So, it is constant. Now, correction of constant errors. One way of reducing the size effect of constant error is to increase the sample size until the error is acceptable. Another way is to subtract or adjust by the non-constant error value. We know in the previous situation, the error of the weighing valence is 0.5 gram high. So, whenever you are taking reading for the next time, you have to deduct 0.5 from the observed value. So, this is a way to correct the constant error. Now, the next category, that is the last part of the discussion, it is nothing but proportional error. I already mentioned the fact that constant error and proportional error are another classification of the systematic error, and we are now focusing on proportional error. Proportional errors depends on size of the measured quantity, but you keep the fact that constant error independent on size of the measured quantity. Proportional errors decrease or increase in proportion to the size of the sample. Sometimes proportional error may increase with increase in size of the sample, or it may decrease with increase in size of the sample. Inverse or direct relation is possible for this proportional error, but remember, the previously studied constant error has no connection with the sample size. A common cause of proportional error is the presence of interfering contaminants that may occur in the sample. For example, there is an estimation procedure for copper 2+ ion by reaction with potassium iodide. In this reaction, copper 2+ on reaction with the potassium iodide liberates iodine vapors. The quantity of iodine is proportional to amount of copper present in the sample. So, you can estimate copper 2+ by noticing the amount of liberated iodine. However, if your sample contain some iron 3+ as the impurity, iron 3+ also can liberate iodine from potassium iodide. So, the quantity of liberated iodine will be more. That is proportional to the amount of iron 3+ present in the sample. So, if more iron 3+ is present, more and more iodine will be liberated. That may cause high value of iodine concentration, and it may wrongly read as the concentration of copper. So, this kind of error is a good example for proportional error. Use a correction factor or recalibrate the instrument using some standards can account for proportional relationship as well as you can rectify, you can correct the proportional extent. So, use a correction factor or recalibrate the instrument to account for the proportional relationship is the option to correct, to minimize proportional errors. So, in this module, we have discussed different kind of errors and their sub-classification. That's all about the module. Have a nice learning experience. Thank you.